first cycle that we've actually gone over in this class. So this is the citric acid cycle, TCA cycle, or Krebs cycle. The whole goal of it is, right, is producing 2CO2, but you're storing the energy from pyruvate and isoCoA, right, that conversion, as electrons in NADH2 and FADH2, so reduced electron carriers. So we've gone through this part last time, but now we want to look at how do those electron carriers end up with your final, using oxygen as an electron acceptor to make water, and then also to couple that to make ATP. And one thing that's really interesting about this, we'll talk about it in more detail both today and next lecture, is that these two things cannot be uncoupled. So when they use inhibitors to inhibit the proton mode force, which we'll talk about in this final acceptor, you also inhibit ATP synthesis, and when you inhibit ATP synthesis, you actually inhibit this process as well. So I'm just re-emphasizing for myself that I said this was due to Torrance. This is the most important aspect with regard to our lecture today and in general within the mitochondria. And oh yeah, you can see all these dots, right? There are many of these complexes. So the mitochondria is just a powerhouse. And you can see that it does not contain the enzymes involved in glycolysis. So you learned that the enzymes for glycolysis are in the cytosol, whereas the ones, right, the pyruvate dehydrogenase complex and the TCA cycle is in the mitochondria. So there's a separation in terms of where glycolysis happens and where this conversion to fully oxidize pyruvate happens. So today we're going to be talking about electron flow in respiration. So this process that we're talking about here, right, this electron transfer and oxidative phosphorylation, it can also be referred to generally as respiration. And basically, part of how people talk about respiration is oxygen, right, being converted to water, and this is your final electron acceptor. So what we're looking at today is this conversion from NADH, right, these electron carrier proteins, electron carrier molecule, transferring electrons down its reduction potential gradient from one protein where they go into each of the different centers that are allowing this electron transfer to happen, to another, finally to oxygen, so that you result in water. So basically you're going from NAD to NADH and oxygen to water. And so you can look up in your tables actually this E value, and you'll see this one is minus 3.2 and plus 0.82. You're always wanting to go right in this direction in terms of this reduction potential. So if you were calculating the free energy, again, these are things you might enter on your exam, you would know that it's the E0 of the acceptor minus the donor. So if we look at that, right, the acceptor is going to be the oxygen that's taking that final electron, and the donor, right, is going to be the NADH. And so because the donor is in the opposite direction, but by convention we write it this way, you always put minus the E of the donor. So this is review, right, from the very first lecture. So that very first lecture, right, comes up over and over again because it's the basis of all the reactions that are happening. So in this case, and if you are having trouble with this, right, so this is minus a minus is a positive, and you get 1.14 volts. So then you would need to be able to calculate the delta G, should have the 0 prime there as well. So that's minus the number of electrons times Faraday constant times this change. And you get 2 electrons, right, in this equation. The Faraday constant is here, and you always want to make sure you have your units. So like if you were doing this on the exam, you're going to be writing it out like this, because you won't have calculators, so make sure you're using units, and then times this delta E. So this ends up being minus 220 kilojoules per mole, right? That's a lot. This is really highly exergonic, and it's really very favorable in generating a lot of energy. So an important thing about this is we talked from the very first slide that we're going to be coupling this electron transport to ATP synthesis. So one thing it's kind of good if you continue in biochemistry to have on the top of your head for the rest of your life is actually what's the delta G for ATP synthesis from ADP. And depending upon like the amounts in the cell and stuff, it's usually 30 to 50 kilojoules per mole. So this is sufficient for ATP production, right? You actually have more than enough. So those are, it's just the type of thing, you can look it up in your book, you have that number. We're going to talk about it again as we couple it to ATP. So I have these carrier proteins, but right now they're just basically like black circles with letters. So let's look at them. So the first thing I want to show you is actually this the electron potential. So these are the standard reduction potentials of the carriers, and we're going to be passing electrons down. Okay. So you can see that these p values, right? We're actually going right like this. So you're getting increasingly positive, right? So when you look at this order, when people were trying to figure out the electron transport chain, they did actually have access to standard reduction potentials. And if you were looking at this, you would have access. And so you could line these up, right, as we have here, based on the delta E. It's from more negative to more positive, and you could say, if someone said, this is what we have, what is the order, right, and you have like different numbers, you can put them in order. But you might not be right. Can anyone tell me why you might not be right? So the key here is this. Yeah?
So those are standard potentials, and in the cell, it's not necessarily standard conditions.
Yeah, I love how loud you were. So I don't know if I'll repeat, but basically, this gives you a good clue that these are based on standard, right? So that zero there, they're not the actual conditions in the cell. So the actual conditions in the cell might be a little bit different, and so you don't know for sure that that's the right order. So again, the type of question you could get would be, given this, you don't know the conditions in the cell, how would you order them? If you were just given the all different order with the E's, right? How would you order them? So people ended up doing, so this is basically just saying what I just said, that the standard reduction potentials suggest the order, but they may not reflect the conditions in the cell. So there are a couple ways to actually experimentally look at this. And so the one we're going to focus on is the use of inhibitors or drugs. So basically, here, these components, right, are the NADH, ubiquinone, which will go into each molecule in a minute, which is Q, the cytochromes B, C's, and then finally A, and then your final, right, oxygen, which is accepting those electrons to make water. So in this Stoic diagram here, which is also discussed in the book, when it's blue, it's been reduced, and then when it's red, it hasn't yet been reduced. So basically, if you have the full thing happening, right, it would all be blue, and the oxygen would be then reduced to water, okay? And so what you can do is you can actually start adding inhibitors. And so if you add this inhibitor rotenone, it actually only NADH was reduced. And so only it is blue, the rest was actually still oxidized. So we know that, which we already knew, but we know that NADH is at the beginning. Then you can sequentially add inhibitors at the different stages. So here, adding antimycin A allows the quinquebiquinone to be reduced, cytochrome B, but these others are still oxidized. So it's just confirming the order. And then finally, at the very end, there was an inhibitor that blocked this final transport to oxygen. And all of these were reduced except for oxygen at the end. So inhibitors are really useful in the study of the mitochondrial electron transport chain. And I don't think we'll get to it today, but next lecture, they're also then important in discussing uncoupling or coupling of the ATP synthesis and the proton motive force. And it's basically how they show that they are really, really tightly coupled. So let's look at these molecules. So you're going to see it as Q. This is ubiquinone. So we have this ubiquinone, right, this quinone structure. And in this case, it's fully oxidized. And then here, when you have the hydrogens, right, it's fully reduced. And this can also have a semiquinone radical. So basically, if you have one electron, you have the semiquinone radical, right, the radical QH. And then if you have it fully reduced with 2 electrons, you have the QH2, and that's fully reduced OH. So 1 electron, 2 electrons. And then this is the isotenoid chain, just to point it out. So there are a lot of important features of this molecule. And basically for this, I wouldn't have you memorize like this whole structure, but if I gave you, this part of it, you would need to be able to show me what the radical was and what the fully reduced form was. And then these are the really important features of this molecule. So the reason that this part of why this is so lipid soluble, so this is a really important feature, is that it has this nice isotenoid chain. So whenever, you guys already know this from chemistry and probably the first part, but there are 10 of these, right? So this is a really nice long hydrophobic chain, this isotenoid chain, making it lipid soluble. It can actually diffuse in the membrane. So it's in the membrane, only in the membrane. It's very hydrophobic, but it can move in the membrane. So this is like a key molecule in this whole process. And bacteria and plants also have very, very similar structures. We're not going to go into detail, but in bacteria, menaquinone, and in plants, phyloquinone, that also act as electron acceptors in electron transport chains that are very similar. So it's this structure with this isotenoid chain that makes it very hydrophobic, lipid soluble, freely diffusible, and it can take 1 or 2 electrons, and it's also actually taking hydrogens as well. So it's able to transfer electrons and protons, can accept 1 or 2. Now, we also talked very generally when I showed you that ABCD and I showed you the reduction potentials, we mentioned cytochromes. So cytochromes come in a lot of different forms. So it's kind of hidden in these slides: B, type C, and type A. Again, you want to just recognize this general porphyrin structure where you have it's a heme-like structure, or we call it porphyrin structure, and you have iron that's coordinated in the middle, and basically it'll be reduced from Fe3 plus to Fe2 plus. So in every case, right, it's 1 electron, right? So you have Fe3 plus, you add an electron, it will be Fe2 plus, okay? So in this case, there are 2, the B type and the A type are tightly bound to the proteins they're associated with, and the C type is covalently bound. And it's via these bioester groups here. So one of the things that you want to know is that, and it's a little bit hidden, I guess, here, but a major point is that the reduction potential of these, you can't just look at it and say, oh, I know what it's going to be, because it depends on the exact association with that protein, okay? So when we have that series, it's been determined experimentally with its protein. And it's different for each cytochrome. So here we talk generally, right, about the structures of ubiquinone. We've already talked about NAD, and then the cytochromes. And then the next thing that we're going to talk about is actually protein complexes. So it's all about transferring these electrons, but there are protein complexes, which I just gave you a hint at because the cytochrome, that structure, right, is associated with a protein complex that facilitate this. And there are actually 4 of these complex 1, 2, 3, and 4. We're going to talk about each one, and then we're going to pull them together. And so you'll see that they have different prosthetic groups that allow for electron transfer. So you can have this FAD, FMN group, right, which we talked about, again, the first lecture, a little bit throughout. Iron sulfur clusters, I'm going to show you in another slide or two. Again, iron sulfur can be reduced or oxidized, right, to facilitate this. The heme has that iron that can be reduced or oxidized, and there's also hemes that have copper associated with them. Again, you can have copper in Cu2 plus or Cu3 plus 4. So I still have a periodic table by in my office because it is the foundation of so much of biochemistry and of chemistry, and you can actually predict what type of molecule would be used in reactions if you know your periodic table. So it's great. You have that. If you have an exam here, it could actually help you. Okay. So I talked about in that last slide, right, the iron sulfur clusters of proteins. And so they can be a couple different forms. And you don't need to memorize this, I'm just showing you this, right? That you'll have the cysteine coming from the actual amino acid, right, of the protein, and then that can be coordinating an iron. Again, it can do it coordinating a group of irons, and then it can be coordinating in a more sophisticated structure as well. And all of these, again, they'll have slightly different electron reduction potential and characteristics based on the relationship with the protein and that particular center. So we're going to move into the complexes now. So the first complex is complex 1. Oh, yeah. So a really important thing that we'll start with is orientation. So we have a matrix side, right? That's that inside, that soluble space. And then we have the intermembrane side, the P side, right? So that's the place between that inner membrane and the outer membrane, right? So here, right, you want this to be going out. So you have your NADH ubiquinone oxidase. I'll often just be calling this Q. So this complex is partly in the membrane and partly in the matrix side. And what happens here is that you have NAD coming in. I think I have something wrong here.
It's reversed.
Yeah, I'm sorry.
It's different on your next slide.
Okay. I'll just go there. All right. I'll have to fix this. I apologize. So basically, what's happening here, and you guys should be able to. I apologize about that. So you would want to catch me on it. I just saw it myself here, but one thing you know is, right, what was coming from the TCA cycle, it was NADH, first of all. And then secondly, you're donating electrons, right? So you're not going to be donating an NAD+. So if you ever see something like this, right, it could even be a question, like maybe I could use this to my advantage. What's wrong here, right? And you would be like, oh, you can't donate electrons from NAD, and also what's coming from the TCA cycle is NADH. So basically you have NADH, and it's being, and I will fix this before posting it, it's being then oxidized to NAD+, and those electrons are coming in to this FMN complex, okay? So then they're being transferred. So whenever you see on these slides blue, it's the electrons, and then black is for the ubiquinone, or Q. So these electrons are being transferred through the FMN, which is a flavoprotein, this flavocyte. Again, the first lecture has this. Then it goes through a series of iron sulfur centers in the complex, and then it keeps going, and then finally it comes to transfer to the Q, which is ubiquinone. And in this case, you're getting 2 electrons, so you're forming QH2. That can then go into the membrane and be diffused through the membrane to go to the next site. At the same time, we're actually having transport. So whenever you have Q being reduced to QH2, you have hydrogens coming in, so you'll always see hydrogen coming in. And then we also have an associated flux of, or transport of H plus going out. So what's happening is you have a transport, a proton gradient being established, and you have a charge being established. So this is positive, and this becomes more negative. However, crazily enough, right, so if some of you want to win the Nobel Prize, this is still open. The mechanism of hydrogen transport is still not established, right? We've known about this complex for so long, it's still not definitively established. So we just went for the first part of the path, right? So that first part of the pathway is NADH. For those of you who just walked in, this is wrong, should be NADH right here, just like this. Transferring electrons all the way up through iron centers and FMN to Q. Now we have QH2. We've started establishment of the proton gradient. We don't know exactly how that happens. Now we go to the next step, which is complex 2. So complex 2, so here's 1 and here's 2. So what I'm showing you is the level that I want you to know. Your book has a more detailed picture of this. So you're on, here's the matrix side, here's the intramembrane space. So we had NADH converted to NAD+, it's correct. Going to FMN, going to the iron sulfur complexes, reducing Q. We're not showing the hydrogens coming in here or the protons, the proton gradient, but that Q, we're focusing on electrons, is reduced, right? So you get QH2, and it's freely diffusible. So basically, it's right here, and you're getting succinate being converted to fumarate, passing electrons to FAD, FES, another Q, which we'll see in a second, and then that forms more QH2. So what this is showing you here is, it's can be a little bit misleading, so we're going to look at it on the next slide and you'll see more drawings. Basically, we'll have another Q coming in here to make QH2, but it's just showing that, like, then all of these QH2s, it's freely diffusible, and so it can also be over here to move on to the next step, or to be available for binding here. So let's look in more detail at this complex 3. Sorry, so this is complex 2. So now let's look in more detail at complex 3. So for complex 2, this is the very basics of what you need to know. So for complex 3, you have electrons transported from QH2 to cytochrome C, okay? So in this case, right, you have your QH2, and then here, and we're gonna go through this, I know that's a lot here, and it's gonna be transported to cytochrome C. So there's a whole cycle called a Q cycle, so we'll talk through it. So there are always 2 subunits that form a dimer for the cytochrome 3 complex. And one of them first acts, it's called at the N side. So there's 2 positions where quinones combined. One is in the N position and one is in the P position, just because this is closer to the N side and closer to the P side. So what can happen here is that your quinone will come in, so you have this Q, and then it's reduced to the radical form, right? So that's with 1 electron. And it gets that 1 electron from the QH2 that it got from the diffusible membrane from the first 2 steps. So that QH2 comes in, And one electron from it goes to Q to make the radical. So if you were confused about how many electrons, you would know that this only means one electron, right? And here you know because of the H2 that it has two. So we're going to first be talking about the bottom part of this, and then we'll talk about the top part. So for the bottom part of it, you're having one electron, and you're reducing Q to the semiquinone radical, dot Q minus. That dot Q minus, this is just showing you like the second phase, or like what happens next within the protein. It can then go into that same spot. Okay, so now it's residing here. It can take another electron. Hydrogens are also coming in, but it can take another electron from QH2, so the second QH2 is coming in, and it's then fully reduced. So one more electron makes it QH2, and now that's really diffusible. So you have two different ones coming in. The first QH2 donates one electron, it makes the semiquinone radical. That moves into position to accept the second electron from another QH2, forming the fully reduced QH2, and which is diffusible. What's happening at the top? Okay, so at the top, QH2 is coming in, right? One electron came down, so it only has one more available. That's going up through the iron sulfur center. So an important thing to remember, so this all connects, so I'm going really slowly through this part, is that those iron sulfur centers and those the cytochrome B centers that I showed you, right, they can only take one electron at a time. So while one of these electrons is coming down to Q, one is going up to the iron sulfur center, then it's being passed on to the heme center of the cytochrome C1, and then finally to cytochrome C, and then that's reproduced. So one at a time, one is going up, 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 and one at a time, it's going down to form that radical. The second one comes in, it fully reduces the radical to the QH2, and then comes up here to reduce another cytochrome C. So you would have two of these coming in, you would have two cytochrome Cs reduced, and the formation of QH2. Meanwhile, right, this is, because this is actually donating, it's being converted to Q, right? One electron's going up, one electron's going down, so the QH2 here is going to Q, and then QH2 is being regenerated through this other site. So these are two separate sites, the N and the P. So as this is happening, you have hydrogens that are being released. And they're being released only, in this case, you have 4 released on the intramembrane side, okay? So again, this is forming that proton gradient. And in your book, they use the word vectorial, or vectoral. It's basically just saying it only happens in one direction, right, like a vector and not. And so it's only happening on this P side, right? So you're having the hydrogens move to this side, and you're, again, reinforcing that proton gradient. So if you look at the whole thing of what happens, right, so we can look at we can look at each one if you want. So QH2, right, plus Q, plus the cytochrome C that's oxidized goes to Q plus the Q semiquinone radical plus cytochrome C1 that's reduced, right? Because in this case, you had one electron reducing this, and that one electron came up here, one electron came down here to make the radical, and then meanwhile, QH2 was converted to Q, giving you Q, right? That's where the 2 electrons came from. And your end product was one cytochrome C. Here, when you come in on the second part of it, to summarize it, you now have that Q going to QH2, And then you have the QH2 here going to Q, right? It's donating 2 electrons. 1 electron comes to cytochrome C1, which is reduced. 1 electron is provided as power here. So the net equation is just QH2 goes to Q, the cytochrome C oxidized to reduce, and then the protons transfer. So we ended this part right with cytochrome C1 being reduced and with Q and QH2 available, right? But then not being Q. So from here, right, this is the final part where we're connecting cytochrome C to oxygen. So this has a number of subunits, so many, like over 10, but there are 3 that have been experimentally shown to be the most important, subunit 1, 2, and 3. So what we want to look at here is basically the electron transfer in terms of what's going on, and then we'll put it all together. So in this case, right, you have the electrons that are donated from cytochrome C that was reduced in the last step. They come into this subunit 2, where they're actually, this has a copper, and then it goes to a copper iron center and heme center, goes to another copper center, and then oxygen comes in and as the final acceptor, and then it's converted to water. As part of this, so for this, right, you mostly, if you were thinking about it, you would just want to know, right, that these would have a series of reduction potentials that would be allowing this electron transfer to happen. And you have a half O2 coming in with H plus as a substrate. So this is specifically saying substrate because you need it to form water. So this has been drawn both ways. Sometimes we just put oxygen and then we double the substrate and then have 2 H2O, but here I'm showing it as a half oxygen. Okay. So we have 2 coming in for the substrate, and then we have a pumping of 2 hydrogens. Again, this mechanism of pumping is still not known. Yeah?
Could you please clarify the difference between where the FeC, the iron copper, is pointing to?
This one? This one?
Center.
The complex.
Is that the whole?
So yeah, basically it's going to this this copper in subunit 2, and then there's this larger complex center. It's being transported to this heme alpha, and then there's another heme alpha 3 here associated with the copper B. So then it's being transferred to that as the oxygen comes in.
So the whole thing is that?
Yeah. Did that help? All right. So if we put it all together, we're basically looking at transfer of energy to a proton gradient, and then the proton gradient is what's going to be driving ATP formation. So if we look at this, here we have complex 1, complex 2, complex 3, and complex 4. So complex 1 is about NADH going to NAD, here it's correct again. You donate the electrons, it goes to Q to form QH2. You initiate, strong initiation of that proton gradient. QH2 goes over here, and you actually have really mostly formation of QH2 from Q within this second complex. The QH2 goes to QH2 in 3, and we have here the transfer to cytochrome C, which is reduced. And this was this whole series where we went back and forth, right? There was this is really simplified, but we have the 2 different sites, and then we went back and forth. One thing I should clarify here is that it might not have been as clear because I said it kind of quickly with 2, is that this is mostly about formation of QH2 here. And then you also get QH2 coming from the first complex. So that can serve as the QH2 that you need to come in for cycle 3. Okay. So then for complex 3, Again, there were these two different Q sites, QN and QP, that series of, basically happenings, that results in the reduction of two cytochromes. That cytochrome, and this is why I put this slide up, is to bring it all together, but to remind me to tell you that this can actually, it's kind of a soluble protein. It can move and then be associated with 4. So it can actually bring these electrons over to associate with 4. We're artificially showing it, right, as like linear, but really they're all, more closely next to each other, but still, this is able to freely associate with the next complex, which is the whole point here. So once you have that association, you're actually carrying those electrons from cytochrome C to then finally be passed on to oxygen, and then oxygen is accepts the electrons to form water. So if you look at the protons that are formed, right, you have 4, and 4 is 8, which is 10, on the P side. So you have this strong proton gradient. And you also have a difference in charge, but we're going to talk about that more in a minute. But you can see, right, that you would not only have the protons, but you would also have this be more negative and this be more positive. So you'll have a difference in charge. So you're going to do an isotope.
A ver si puedo ver.
Fíjate ahí, échale ganas. With special properties are going to the goal of 2 for now. They can't accept 1 or 2 electrons, huh? Is that ubiquinone or no? Because remember, is that the one where it separates us because of that long fatty chain?
I'm thinking yes, because it's
I think it's all the above, no? Because I remember she said that long chain of it is
yes.
hydrophobic and makes it very lipid soluble, and it can diffuse.
Really?
the
She said
membrane.
that?
Remember in that one chart?
They test them.
Hey, Sue.
Really?
I thought that was
Madison, what do you think? E?
wait.
Yeah.
E.
Yeah.
E. All right, cool.
Say it with confidence.
E. E.
That was like a green, so yeah, that sounds perfect.
Pretty
Hey.
sure.
E.
Because if it's in the membrane, it has to be hydrophobic.
Yeah.
Yeah, because I remember she talked about that one
Yes.
part.
Good, you have good memory.
You remember that? I was looking out.
I was like,
I didn't know what ubiquinone was, but I saw that and it's like 2 electrons, and I was like, all right, lipid soluble, that long chain is going to be. We just double click then. That's okay.
I always click like 5 different times just to make sure it went in.
That's okay.
You do have a
We did it, people. We did it. We did it.
that's the easy question. Like, I was like, I should go ask like something complicated.
She
I'll
could
take
have
it
asked
though.
something way more complicated.
Yeah, I'll take it.
All right. 5, 4, 3, 2, 1. All right. Oh. Wait. Oh. I don't know. I'm a bad. I couldn't stop it. There we go. Okay.
Oh, people were like,
We could have like.
oh, those 3 people didn't do it.
There's 3 people. Last time was so bad though. Last time was like 10, 20 people that don't like get it.
No, but she actually, she showed the answer before she even clicked the top.
I gave you that question. is
That's
that
what's
it
amazing.
You had time to like to the right answer.
transport chain. And sometimes when you're drawing it, like if you're just drawing it, you won't actually realize all the properties in it that make it essential. And so whenever you also think about phenols, right, they have a lot of special properties, and then that isocanoid chain is helping you
Almost.
hydrophobic and lipid soluble. All right, so now I'm gonna close this and get it out of your view. We're not done.
That was funny. I wasn't paying attention, but she did
So
that.
we're gonna talk about something fun now. I mean, all of it is fun, right? We love
Yeah,
it.
super
But
fun.
I'm gonna,
I'm thrilled.
What happened?
She said it's super fun.
It's interesting.
She's gonna give us something super fun. She's gonna show us something super fun, and all of it is fun.
Skunk cabbage.
we're gonna talk about two plants. So this is kind of like, an alternate pathway that can happen. And we'll look at the details of how this happens. It's called the alternative oxidase. And plants actually can do this, and it's a way of producing heat. So there are two plants that you guys might know well. Who has ever had experience with the eastern skunk cabbage? Oh, okay. Where I grew up, it was like all over. I grew up in Connecticut for most of my life. And how about the voodoo lily? It's also called the corpse plant, the arum lily, right?
Heard about it.
We even have them sometimes at Botanical Garden. We have one that was actually flowering. So why do you think I'm putting this here and talking about thermogenesis, right? What's the clue? We've been learning a lot. I feel like we're teaching like Latin word power. So thermogenesis. What am I
know.
talking about here? Yeah. 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 So thermo, heat, genesis, forming, right? So these are heat forming. And the thing that's amazing about them is that they, like for the voodoo lily, it can actually heat up to 20 to 40 degrees Celsius above ambient temperature. So this is just crazy. And it happens basically when you have flowering. So this has a special type, you're not plant biologists, but basically this spadix has all these tiny little flowers. And when it heats, when it's basically ready to be pollinated, it has this heating of 20 to 40 degrees Celsius, and it produces this odor that's like rotting flesh. And so that's because it actually wants flies that often are feeding off of recently dead like mammalian corpses, right? It wants them to actually come and pollinate it. And the other thing is that usually because it's on things that are hot, it will, they think that also maybe even just being hot itself is also another, like if the fly or whatever is actually sensing temperature, it might like both the odor and the temperature. So some of those details are still being figured out, but they know that it's an attractant, and they're figuring out exactly which of the molecules are actually attracting them. And one thing that's kind of cool in our generation now is that a number of places, including at the Botanical Garden, in the hot room, the tropical room, we have one of these. And then also actually the Plant Genus Fresh Center in Albany has one. And so it's literally like people are so excited by these that we will post that announcement when you can come see them. And at Cornell, they also have a strong plant biology department, and they have one, and they actually had a webcam on it. And so it was really funny because the length of time when it has the most intense smell is not that long. And so you could actually tell by looking at the webcam, like you'd see people go in and kids, and they're like, But then, over time, right, it's only like a day or so, and then you could see people weren't having such a strong reaction. So I haven't looked recently to see if you can go back and see it from a couple of years ago, but if you ever get an opportunity to see this when it's blooming and smelling, you should certainly go. And you also want to know that the smell does not last for the whole period, so you really want to get in that window. So basically for the voodoo lily, it's about attracting pollinators. And then for the skunk cabbage, it's both so it comes up actually really like in the end of winter when there's still snow typically. And so to get through, they think it's both about getting through the snow and then also for attracting pollinators. So how does this happen? So this is plant specific. So it's actually bypassing, it has a lot of so this is actually two enzymes that are unusual, and then the alternative oxidase, which is unusual. So it's not using this complex 1 or 3 or 4. So instead what's happening is it's taking NADH coming in on this side of the membrane, and NADPH on this other side of the membrane, on the P side, and it's using the reduction potential from both of those to actually reduce Q. It's just not showing it in the picture. And then the reduced Q is what's then, again, so QH2 serving to then reduce oxygen to water. And because this is not coupled to proton gradient and ATP synthesis, you actually get a lot of heat produced. So there's also, there are other plants that use this as well, and very particular conditions, but those are two really fabulous examples that I think you'll get to see. So I'm just going to do 2 more slides and then we'll be done. So I'm just re-emphasizing, right, that we went all the way in normal electron flow from NADH to water, and then in that process, right, we had a big change in the reduction potential, and we had a really big delta G that was highly negative, and that's a lot of energy for ATP production and for pumping basically those protons out of the matrix that's driving the ATP. So next time we're going to start with the Penny-Osmotic model and then go into the details of the synthesis.
Hey, you're the real MVP. Oh no, it's still recording.
You also have a Surface Book?